Well, now that we have conditional probabilities, and we also have unconditional ones, which is just the probability of an event without any conditioning, we want to be able to relate the two. And the way to do that is using a thing called marginalisation, so that we can map back and forth between them. So let's go back to our sentence example, try some numbers and try and get some intuition about how we might map back and forth between conditional and unconditional probabilities. Suppose we pick a family at random from the population. So that's an unconditional experiment. I'm not restricting it to the families with 1 children or 2 children. It's from any family. And then I ask, what's the probability that all the children are less than 15 years old? So that's an unconditional probability. We're not restricting it to any particular family. How would you calculate that? Okay, so let's calculate how many families have children, all the children less than 15 years. So we're at 178,000 plus 92 plus 30 plus 8, which is 309,000. Then we calculate, well, what's the total number of families? 344,000 plus 339, blah, blah, blah. And so that's 1.19 million. And so it's the ratio, right? It's the fraction of the overall families. Out of the 1.19 million families, 309,000 have all the children less than 15 years. So the probability, assuming when we do an experiment where all outcomes are equally likely, so we've chosen we've done our count out experiment so that the family we pick, we're not biased, all families are equally likely, then the probability will be 0.26. So you see what we did? We added everything up. So let's write the same thing slightly differently. Let's write, this is the fraction so we've got our 1.19 million families. This is the fraction of that who had just, with 1 child, and all those children were, and the child was less than 15 years, 2 children and both were less than 15 years, 3 children and all were less than 15 years, and so on. So all we're doing is taking the number here and dividing it by number of families of 1-child families with the child less than 15 years, dividing it by 1.19 million. And then if we look back, what we really were doing, let's go back to the previous slide. So what we're doing is we're taking this 309,000, remember we're dividing it by the 1.9 million, so we divide that value by 1.19 million, that value by 1.19, and so on. And that's the same, so that's those fractions that we had in the next table, and we just add them up and we'll get 0.26. So here we are, these are these fractions, we add them up and we get 0.26. And the reason to write these as fractions is because then they're probabilities, right? So what's this first probability? It's a probability. Let's define our events, right? Fi is the event that we have I children, so F1 is that we have 1 child, F2 that we have 2 children, F3 that we have 3 children, and so on. And let E be the event that all the children are less than 15 years old. So this is the probability that all the children are less than 15 years old, and you had 1 child, probability that the children are less than 15 years old, and you had 2 children, and so on, right? And we know these fractions from our table, we just add them up and we get to 0.26. So you see we're just adding up all of these probabilities and we get to the unconditional probability. So we're nearly there. So here's the general way to do marginalisation. Suppose we have a set of events that are mutually exclusive, so there's no overlap between them. And they also have to add up to all possible outcomes, right? So remember we had no children, 1 child, 2 children, 3 children, more than 3 children. So we have to add up to all possibilities, we can't leave any gaps. Then if we're interested in event E, we just add up all these intersection with each of the individual events, right? So E intersection 1 plus E intersection 2 plus E intersection up to Fn. We just add up these. And remember, these are very closely related to our conditional probabilities. Let's jump past this. So this proof again here, you don't have to believe me that this thing here holds, this marginalisation relationship holds. You can convince yourself, this guy here. This is the proof for it. You see, it's 1, 2, 3 lines to prove it. It's very straightforward. So the reason I give the proofs isn't it's not because you should memorize them. Memorizing them, there's no point in that. You're going to have an open book exam anyway. The point is so you can understand the logic and see the reasoning, and also just to convince yourself. One of the nice things is you don't have to just believe me. You can go convince yourself. So although I'm going to skip over it here, stop and go back and just check that you understand these various steps, because they're very straightforward and it'll help you understand what's going on. Now there's a special case of this guy, this marginalisation up here. Remember, we're going to combine this with the chain rule, right? So let me just look at the first line here, because this is the chain rule. So the probability of E intersection F1, if we apply the chain rule, remember that just comes from the definition of conditional probability, is equal to the probability of F1 given E times the probability of E. And then the probability of E intersection F2 is the probability of F2 given E times P of E, and so on, right? So you can see there's a close link between these quantities here and conditional probabilities. So here's an example down here, which is going to be it's certainly not the only one, but it's one that comes up again and again, so it's worth just pointing out, highlighting it. So suppose we're interested in an event E, probability of an event E, and then we can always write it as the probability of E conditioned on F. So the probability of E given an event F has happened times probability of F. So that's the probability of E intersection F plus the probability of E given that F didn't happen times the probability of F, the F complement. So that's the probability of E intersection F complement. And we can take this guy here, the probability of F didn't happen, and simplify it a little bit and write it as 1 minus the probability of F, right? So here we've only got 3 quantities that we need to know to calculate E. So the probability of E given that F happened, probability of E given F didn't happen, and the probability that F happened. Then we can combine those conditional probabilities and get the unconditional one and map back and forth. And so this is a special case with just 2, where we've just got 2 entries, but of course you can do it more generally. And marginalisation is really handy. We use it all the time. So here's some examples. So suppose we roll 2 coins, right? What's the probability that the first coin is a heads? Now we've flipped it, right? Before we were conditioning on that, we assumed the first coin was a head. Now we're saying, well, what is the probability that the first coin is a heads? So here's a nice way to do this, calculate that using marginalisation. Suppose let E be the event that the first coin is a head, F1 the event that the second coin is a head, and F2 the event that the second coin was tails. Then we know the probability that the first coin was heads is the probability of E intersection F. So it's probability that the first coin was heads and this first coin was second coin was heads, plus the probability that the first coin was heads and the second coin was tails, right? So it's really trivial, right? You can see when I say it in English, the equations make sense. So the probability the first coin is heads is a half, because there's only 2 options. It's a fair coin. Probability the second coin was heads is a half, so we multiply them and so on. So we get half as a probability. Let's try another example that we'll use again shortly. And I'll say HIV here, but this could be a COVID test or other things. We'll come on to some other options later. So suppose we've got an HIV test that identifies HIV 98% of the time. So what does that mean? That means if you have HIV and you take the test 98% of the time the test will be positive and say you have HIV, and 2% of the time it'll say you don't. So that'll be an error. So it's pretty accurate, right? 98% of the time it's going to be correct. But suppose it also has a false positive rate of 1%. What does that mean? That means you don't have HIV, you take the test, 99% of the time it will say negative, you don't have HIV, but 1% of the time, even though you don't have HIV, the test will be positive and say that you do have it. So that'll be an error. So let's ask the question, what's the probability that you test positive? Suppose you're doing a dragnet test across of everyone in the population. So it looks like a decent test, right? 98% of the time accurate and only a small number of errors. Now, if we plug in some numbers for Ireland, so roughly 0.2% of the population is HIV. So let's call E the event that you test positive, F1 the event that you have HIV, F2 that you don't. So then 0.2% written as decimals is 0.002, right? 0.2% is 0.2 divided by 100. So 0.002. So that's the probability that you have HIV. And this is the probability that you test positive given that you have HIV. This is the probability you don't have HIV, and this is the probability you test positive given that you don't have HIV. So that's the false positive. Add them up and you get 0.012, which is 1.2%. You can see that's roughly combining. So if of the 0.2% population, you get most of them, right? 98% of them. That's the 0.2%. But but you also get this 1% because you're testing loads of people who don't have it, but you're going to catch this 1%. So actually, it's quite a big number that you end up finding positive, bigger than you'd think. It's not 0.2%, it's 1.2%, which is a lot bigger, it's like 6 times bigger. So even small numbers of errors here, this false positive rate can be quite significant when you're testing many people, Let's try another example. Suppose we roll 2 dice. Let F1 be the event that the first dice comes up 1, F2 that it comes up 2, and so on. So F3 would be that it comes up 3. Let E be the event that they sum to 6. So what's the probability that they sum to 6? Of course, it's just 2 dice, we could enumerate it, but let's use marginalisation to do it, right? So, and notice here, whereas in those other examples we were summing 2 things, marginalisation works even when we're summing multiple events, right? It's not just for 2 events, not F and F complement, but for much more complicated setups. So we've got the marginalisation tells us the probability that the sum is 6. It's the probability of the sum of 6 given that the first dice comes up 1 times probability of the first dice comes up 1 plus probability of the sum to 6 given the first dice is 2 times the probability of the first dice is 2 plus blah 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 probability that the sum to 6 given the first dice is 6 times probability of the first dice is 6. Now the probability of the first dice is 1. They're all equally likely, right? So it's 1 over 6. Now the probability that they sum to 6 given the first dice was 1 is 1 over 6, because the only way that can happen is if the second one comes up 5. There's only one way that can happen. The probability that they sum to 6 given the first dice was 2, there's only one way that can happen, right? That's if it comes up a 4. So there's only one, and so on. So they're all 1 upon 6. So it's nice and easy. Oh, the last one can't happen though. You have to have a little bit of care, right? So the probability that the sum to 6 given the first one was 6. Well, the second one has to be a 1 or bigger, right? So it'll have to sum to 7 or higher. So the probability that the sum to 6 is 0 there, right? So what we end up with is we sum 5 for each of these. The first 5 we get rid of the last one. This is the probability that the first dice comes up 1, 2, 3 and so on. And this is the probability that they sum to 6 conditioned on that to make it 5 over 36. And we can, because this is a nice simple example, we can double check it. here's the actual event that summed 6 is we came up with 1 and a 5, a 2 and a 4, and so on, a 5 and a 1. So we know the E has 5 elements. Sample space is 36 elements, so we get 5 over 36, and it all agrees and makes sense. So we can calculate it in different ways. But you can see this, using marginalisation, we can move between these conditional probabilities and the unconditional probabilities. So it's a way of mapping back from conditional probabilities to unconditional ones. So it's quite important.